Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our lesson for 7.3.1. This is where we are going to pull everything together with our scatter plots and our creating of equations. And we're actually going to start looking at situations, creating a line of best fit, identifying the rule for that line of best fit, and then using that rule to answer questions about the data and the situation that we have before us. So let's get to it. It says, previously you have learned to find and extend patterns in data and to make predictions using rules, equations, and graphs. Today, you will apply these mathematical tools to a real situation in which your data does not make that perfect pattern. Okay, so it says Arlie's bike ride. To prepare for a 30-mile ride for charity, Arlie has been biking every weekend. To predict how long the charity event will take her to complete, Arlie has been keeping track of her time and distances. She tries to ride at a constant pace, but of course that's not easy to do, right? You have to stop for stop signs, you got to stop for cars. You're going up hills, down hills, around curves. You're going to have to speed up and slow down on a natural bike ride. Okay, so it says, would a box plot, scatter plot, or a histogram be most useful in helping Arlie make this prediction? Since we are talking about two variable situations where you have distance and time, and you're trying to see how the amount of time affects the distance, or the distance you go affects your time, or your rate of speed affects either one of those, I feel like your scatter plot is your best choice here. A box plot's good for when you've got one set of data and you want to find averages and the spread. But when you got two kinds of data, we definitely want to use the scatter plot. Okay, so here we go. It says, considering that Arlie is trying to predict how long it will take to complete the ride, which is the independent variable and which is the dependent variable? All right, so this is always the hardest part, is trying to figure out which variable is which. Which variable goes on the x-axis and which variable goes on the y-axis when you're plotting these points, right? So let's read this again. Considering that Arlie is trying to predict, she's trying to predict how long it will take. We're going to make the time, or how long it will take, is going to be your dependent variable. Because how long did it take? It depends. How far did she go, right? So the independent variable is, in this case, going to be the distance. So you are keeping track of the distances that you are traveling, and you are trying to see how much time did it take you to go those distances. So in this situation, Arlie is assuming control of the distance she travels and then recording the time that it takes her to do it. So the distance ends up being on the x-axis, the independent variable, and the time goes in the y-axis for the dependent variable in this situation. The more you do this, the easier it becomes. But just keep in mind, you have total control of the independent variable. And to answer the question of how much time it would take, when we're saying it depends on the distance that you go, you know that the time is the dependent variable. Okay, so then it says, use a line of best fit to predict how long it will take Arlie to complete the charity ride. Remember that the line does not need to intersect each of the points, and that the line does not need to pass through the origin to model the data. This is something that, you know, I've mentioned it a few times on like homework problems. We want to try to avoid assuming anything about this data, okay? While it does make sense that seems like we should start at 0, 0, because if you go nowhere, you spend no time doing that. Although you could actually, in this situation, be stopped and time will continue going. So I guess you could go nowhere in this situation and still have time elapsing, because time never stops, right? But just go with the data, go with the flow of the data, and see if you can make sense of the slope and the y-intercept in this particular context. That's really the direction you need to go. And sometimes it doesn't make any sense. I don't know why, but a lot of times, if you think about it, there is something that can explain why your y-intercept is what it is. Okay, so what I'd like for you to do is create this scatter plot, create this graph where we need it to go. I guess we need the time to go up to 150. So you decide how you want to count. I chose to count by 25s. And you want your distance to go all the way up to at least 25, and I had mine end up going to 30. So go ahead and pause it and create your coordinate grid and copy down this data right here. And then once you're ready, unpause, and then we can put these points on together. Okay, so I'm going to go ahead and pause, let you pause and get the graph set up for the table copied in your journal. And then when you're ready to move on, unpause. All right, I'm getting ready to go. If you're not done, if you haven't paused yet, pause the video. I'm going to start putting these in. All right, so I'm going to do this in blue. And we said the time is going to be actually the y data, and the distance is going to be the x data. So when I do this, I'm just going to go one at a time. We're going to take the 7. There's halfway point is 7.5, so 7 will be right around here. And then 68. If this is 25, and it's going to go 55, 60, 65, 70. So 68 is probably going to be somewhere around there. And you do not have to worry about getting this perfect, but you want it to get pretty close to where you would think it would go. Okay, so I've taken care of this one. Now let's do 17. So 17 is going to be around here. And then 88. What is 88? So this would be 75, 80, 85, 90. So 88 is going to be about the halfway point. So we'll plot that one there. And then 3.5, this is 2.5 is the halfway, so 3.5 is probably around there. And then 35, that would be 25, 30, 35 is probably going to be somewhere around here. 25 and 150, that's an easy one. That goes right there. And then 14 and 104, 14 is right around here. And 100 is there, so 104 is going to be somewhere around here. And then 80 and 11. 80 and 11. 11's around here, and 80 is going to be somewhere around there. Okay. So we absolutely see a flow to this data, right? And I would think that the line, I mean, actually, let me, let's just create this blue line here. It seems like the flow is going somewhere like, something like that, doesn't it? We want to try and get the number of points above it and below it to be about the same. I got 1, 2, 3 above it, 1, 2, 3 below it. Now this guy is a little bit lower than this guy is high, but still, I think that's a pretty decent line of best fit. Or maybe I'll try and even this out a little bit. Maybe something along those lines. I don't know. It's not easy to get it perfect. And now, actually, I'm going to consider something else. I'm going to consider seeing if I can match up a couple of lattice points here. What if I did this? Would that make sense? The data? Or should we bring it down a little bit more? See, this is the hard part, is trying to figure out where the data is and what should be our lattice points. All right, I'm going to do this. I'm going to choose this. I'm going to say those 2 points are going to be on my line of best fit. And while there are 3 above and 1 below, I feel like that kind of follows the flow of these points. And it's a pretty good balance, right? The distance between those two is pretty close, but this is a little bit farther off. I'm going to go with this. And the primary reason why I'm going with this is because I know that this point right here is this point right here. And I know this point right there is this point right there. So if I take those ordered pairs and I find my slope ratio out of them, then I'm going to be able to find my slope without too much trouble. All right, let's see what it ends up being. Change in y. goes from 35 to 150. So 150 minus 35 is 115. That's your change in y. And your change in x goes from 3.5 to 25. So 25 minus 3.5, what does that end up being? 21.5? 21.5? So let's change this so that it is a decimal number. So I'm going to take 115 and divide it by 21.5, and what do I get? I get about 5.3, 5.35. Let's call it 5.35. That would be our slope ratio. And let's look and see what our y-intercept appears to be. Does that look like it's about 20? I feel like it does. It looks like it's about 20 right there. So could we say that the y-intercept is at 20 so that our rule ends up being y is equal to 5.35 plus 20. So it says here, use the line of best fit to predict how long it will take her to complete the charity ride. And if I'm not mistaken, it's a 30-mile charity ride. So we're going to say the distance for 30 miles, according to this rule, would be y is equal to 5.35x. No. Let's put in the 30 for x, right? Because that's the distance, and see what we get. So let's take 30. Now let's take this number. I'll just leave it like that because that's not rounded off, right? That's exact. So I'm going to multiply that times 30. That gives me 160, and 160 plus 20 gives me 180. So does it appear as if it's going to be pretty close to 180 minutes, which is about 3 hours? I think that's pretty close. If we were to extend this line up, and then we were to extend this, does it look like maybe that would continue going to about 180? I think it does. That's pretty close, right? Because we're kind of made 25s here. So this would be about 175, so 180 is a little bit above that. I think that's a pretty reasonable estimation. Not perfect by any means, but reasonable. All right, now let me show you how if I created a different line of best fit. Let's say I were to choose and just assume that 0 would be the number and have that be my line of best fit. So this assumes that 0, 0, this is a proportional type situation. If you travel no distance, you take no time traveling. So what does this lattice point end up being right here? You have 0, 0, and then you have 15, 100. So that means the distance, the change in x is going to be 15. And the change in y is going to be 100. And what is 100 divided by 15? No. 100 divided by 15. Now my slope ratio is about 6.67. So if I now make this a proportional type of equation, 0.67 times x, and I multiply that times 30, let's see what I get. This times 30 is 200. Okay, so look at the difference here. When I turned it into a proportional type situation, our estimation was about 3 hours and 10 minutes. When we followed the data, it appeared to be about 3 hours or 180 minutes. So is there a huge difference in our answers? Not really. Not really at all. But it did make a slight difference. Okay, so what if I were to move this guy up a little bit? And move this guy down a little bit. Like make this guy have a y-intercept of about 10. Now let's see what we get for an answer. And I'm going to do this in green now. Okay, so we're going to call this point right there 0, 10. And this point here is still 15, 100. So that means that the change in x is still 15, but the change in y is 90, and this becomes 6 for slope. So y is equal to 6x, and our y-intercept was 10. What do we get for this one? We get 6 times 30 is 180 plus 10 gives us y is equal to 190. So these are not all that far apart from each other. The range, remember, this is a prediction. So we could say that the amount of time it should take, we could estimate is anywhere between 180 minutes and 200 minutes, depending on where your line of best fit goes. Okay? So the placement is not going to be perfect. Not every student is going to have the same rule with the same slope ratio and the same y-intercept. But they're all relatively close to each other so that our answers end up being, plus or minus 10 minutes, right? If you call that one in the middle, this is 10 minutes more, that's 10 minutes less. That's pretty close, right? And that's the point here. It's an estimation and a prediction. It's not expected to be perfectly accurate. All right, so sometimes it's more convenient and more accurate to use an equation to make a prediction rather than make a prediction by reading the graph. So we've kind of already done this, right? I just went through the entire process. So I'm going to skip over this. I think we've pretty much wrapped our brain around this entire process. All right, now let's go in a different direction. And I have to be honest with you, I don't really like this problem too much. How much time do we have? Okay, we've got time for this. This is really confusing. In my first year of teaching this, I was really frustrated with the problem. But I've wrapped my brain around it, and notice this little green star right here? I'm going to read this right here after I read through the problem, and we'll make more sense of what this data is telling us. Okay, so it says Westland Workers Union's Health and Wellness Department started a voluntary lunchtime running club. Members kept track of how much they ran each week for exercise and how much their resting heart rate dropped after or over several weeks. Their data is in the table at the right. Note that a negative heart rate change is actually a gain in heart rate, okay? So the way that this works is the healthier people, when they take their heart rate, when they are just resting, like sitting in a chair, not doing any exercise, healthier people tend to have lower heart rates, beats per minute, than unhealthy people. It's like unhealthy people that have like weight problems or whatnot, their heart has to work harder. And so it pumps faster to get the blood going through the system. Whereas if you happen to be healthier and carry less weight, your heart doesn't have to work as hard. So by exercising regularly, and this would be considered cardio, right? When you're running over periods of time, that's good for the heart. And so what you have here is 6. The change of 6 beats per minute means that their rate went down. Like if their heart rate at the beginning was 80, after running some weeks and running 5 miles per week, it's down to 74. Okay, so a positive value indicates a decrease in the number of heartbeats per minute. Right? I mean, this could be more confusing. Okay, so let's go ahead and plot these points on a scatter plot. And well, look at there, I already did it for you. Let's go ahead, take your time. Let me cover this up. Okay, you go ahead and create a coordinate grid where you're counting by ones, and since we do have some values for the resting heart rate that are in the negatives, we should make sure that it's a 4-quadrant graph so you can get into the negatives. Okay, now you're never going to run a negative distance, but you can have a positive and a negative change in your heart rate. So let's do a 4-quadrant graph and plot each one of those points. Now the X value, the dependent variable is your Y, right? And the X value is the independent, which is what you control. So what we're trying to do here is see what effect does running have on your resting heart rate. So this is your dependent variable, so this goes on the Y-axis. So go ahead and set that up, plot those points, and pause. And when you unpause, of course, if you want to just back up the video a little bit. I guess I don't even need to. Just go ahead and copy those down. Unpause when you got everything in there. Okay, so now we have to create our line of best fit. And I see a general flow happening here. I feel like this is the general flow going through this data here. And one of the reasons why we want to identify an outlier like this guy right there is because if you have an outlier, you don't want to be tempted to try and include your outlier with your data, right? It's like you got a pretty clear idea of the flow here, and you've got your data over here that goes through that line of best fit, but this one doesn't really fit in with it. So just leave this out. In fact, you might just go ahead and get, oh, I guess I can't delete that because I've got it locked in there. At any rate, I feel like that's a pretty good line of best fit. And so let's see if we can identify, here's a point right there. And there's a point right there. What is the, what's the slope of this particular situation? The change in y goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the change in x goes 1, 2, 3, 4, 5, 6, 7, 8. So it looks like our slope ratio ends up being 11/8, which if we put into a decimal form, 11 divided by 8 appears to be about, let's call it 1.4. We can round it, okay? Yeah, I think that's fairly decent. All right, so let's answer these questions. Describe the association. Does that look like it's fairly strong association? Moderate to strong. It's linear, and it's positive. So what did I say? Positive and linear. I didn't commit to whether it was strong or not. So just draw a line of best fit for the data. Find the equation for that line of best fit. I'm actually, I'm a little concerned because every time I do this, I come up with a different line of best fit. And hold on. Okay, so let's come back here and let's identify what our y-intercept appears to be at -2. So b is equal to -2. So if we were to create a rule for this, you take our slope ratio times x minus 2. So the rule for this situation should be about y equals 1.4x minus 2. And so if you use that rule and say, all right, predict heart rate change for an employee who ran 10 miles per week. So we'll take that rule, and 1.4 times 10 is 14, and 14 minus 2 is about 12. So we would expect, where y is the change in the heart rate, to have their heart rate decrease by about 12 beats per minute. Okay. So now's the most important part of all of this. Let's interpret what is the meaning of the slope in the context of this situation, and what is the meaning of the y-intercept in this particular situation. So the slope really means that we expect for every mile that a person runs, their heartbeat to decrease by about 1.4 beats per minute. That appears to be about the average. That's the trend for this situation, right? As their number of hours increase, no, the number of miles increases per week that they run, their heart rate change increases, meaning that it goes down. Okay, so yes, so that's the interpretation of that. And what does the y-intercept in this particular situation imply? It implies that being at -2 is that someone who does not do any exercising at all to increase their cardiac health will see their heartbeat most likely increase by 2 beats per minute. Now, that's the interpretation. Does that fully make sense here? I mean, why wouldn't their heart rate just stay the same? I don't run at all, but I do other types of exercise. So does that mean that my heart rate is increasing? I don't really know how that works. At any rate, I think you focus kind of on what the slope ratio means in the context of this problem, and we can start to make predictions. But again, there are limits to this, right? if someone runs 100 miles, like a standard, pardon me for going off on this tangent here, but at some point you can't have no heartbeat, right? We all agree on that at some point your heart still needs to beat. So I think usually people consider between 60 and 80 beats per minute to be that healthy range. And once you start getting over 90 and 100, it starts to get worse. Okay. So, if 80 is the normal and you run 50 miles a week, then what is 50 times 1.4? 1.4 times 50 is 70, minus 2 is 68. Is a person going from 80 down to 12 beats per minute? No, that is absolutely not going to happen. If someone was at 60, are they going to go down to -8 beats per minute? That doesn't even make sense. So there are limits to this, okay? But just in the short term, this kind of a process can be very, very effective for answering questions, okay? So I am going to, we should have a check for understanding where, we can analyze some different scatter plots, and, they'll have some real meaning, add some real meaning to the data, and we'll be able to draw some conclusions based on our understanding of how all of this works. Okay, so let's move on to a check for understanding. Take care. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.